Good morning, and thank you for joining us for the Princeton Mercer Regional Chamber's 26th Annual Albert Einstein Virtual Memorial Lecture. I'm Wari Howell, Director of Events at the Princeton Mercer Regional Chamber, and I'm pleased you were able to join us this morning. Although we transitioned to a virtual event this year, I know you will find the lecture to be inspiring and enlightening. Before we begin, I have some general information to share with you. If you have any questions for our speaker, please use the Q&A box and they will be answered at the end of the lecture. If you experience any technical difficulties, use the chat box, which is being monitored by our staff, and they will assist you. Now, to begin the program, it is my pleasure to introduce Brenda Ross-Dulon, Chairman of the Board of the Princeton Mercer Regional Chamber. Brenda?
Good morning, everyone. On behalf of the Princeton Mercer Regional Chamber of Commerce, Board of Directors, and all of our members, it is my pleasure to welcome you to the 26th Annual Albert Einstein Memorial Lecture. The Albert Einstein Memorial Lecture is presented annually by the Princeton Mercer Regional Chamber. It is the only lecture series of its kind throughout the United States presented by a Chamber of Commerce that features Nobel Laureate speakers. And you are in for an absolute treat today. Without any further ado, it's my pleasure to turn the program over to Peter Crowley, President and CEO of the Chamber.
Thanks, Brenda. I appreciate that. And good morning, everybody. As Brenda said, my name is Peter Crowley. I am the President and CEO of the Princeton Mercer Regional Chamber. And I really want to welcome everybody. We've got a large audience today to the 26th Annual Albert Einstein Memorial Lecture Series. But I do want to make a quick note. Without these four sponsors who have been consistent with us, we couldn't bring this to you. I want to thank Bristol Myers Squibb, Janssen Pharmaceutical, GHO Ventures, and Novo Nordisk. And they've been partners with us for a number of years, and I thank them all. We're also pleased to have the Institute for Advanced Study as our promotional partner for the Albert Einstein Lecture Series. The Institute for Advanced Studies is one of the world's leading centers for curiosity-driven basic research. Since 1930, it has served as a model for protecting and promoting independent inquiry, prompting the establishment of similar institutes around the world, and underscoring the importance of academic freedom worldwide. Robert Dyckgraff, Director and Leon Levy, Professor of the Institute for Advanced Study, will be joining us quickly. Robert is a mathematical physicist who has made important contributions to string theory and the advancement of science and education. At this time, please welcome Robert Dyckgraff, Director, and Leon Levy, Professor. Robert?
Thank you so much, Peter. And it's a great pleasure and honor to say a few words of welcome to all of you on behalf of the Institute for Advanced Study. I was looking forward to welcome you on our beautiful campus in person, but unfortunately the world had other plans. Anyhow, we are thrilled to partner with the Chamber on this Einstein Memorial Lecture, because as you know, the Institute was Einstein's academic home from the time he arrived here in the United States in 1933, fleeing from Nazi Germany, till his death in 1955. He was one of the first professors at our institute. And our founding director, Abraham Flexner, wrote at that time that the center of gravity of scholarship traveled across the Atlantic. And it certainly made Princeton one of the world centers in theoretical physics, and in particular for the study of gravity and cosmology. Now, the past decades will undoubtedly be seen as totally revolutionary in cosmology and the study of the very large, just as in Einstein's days, the development of quantum theory and our knowledge of the very small. And I think nobody embodies this legacy more than today's speaker, Jim Peebles. And if I can put in a pitch, there's no better account of this than Professor Peebles' wonderful book, This Cosmology Century, that was just published by Princeton University Press. Now, Jim is not only a great colleague at the university, he is also an alumnus of IAS. He was a member in our School of Natural Sciences, first in 1977, and then a visitor many times thereafter. And I have the best memories of collaborating with him on the centenary of Einstein's theory of relativity that we celebrated in 2015. Now, the Institute for Advanced Study provides a home for the next generation of scholars, in particular young physicists, whose opportunities actually are shrinking these days because of the economic crisis. And we feel very strongly we must support them so that we can give also in the future space to explore and make world-changing discoveries. So who knows, we might find for you the next Einstein or the next speaker in this wonderful series. So I invite you to tune in to some of our other upcoming lectures this fall, and please check our website, because while the world is closed around us, we are virtually more open than ever, and we're very proud to be part of this wonderful lecture. So thank you all for tuning in.
There we go. Thank you, Robert. I appreciate that. And we're really thrilled that the Institute for Advanced Study is a partner with the Chamber presenting this series. And you should know there's over 500 attendees listening to our speaker today. But that our speaker wouldn't be possible today without the work and the hard effort of a young lady who has been involved with our program at least for the 12 years I've been leading the Chamber. That's Marian Reinster, To The Point Communication. Marian Reinster has been the chair of the Einstein Committee, again, since I've been here for 12 years and before that. We're fortunate to have this young lady work with us, and she's a clear leader in our region. Marian, take it away.
Thank you, Peter. As you know, this has always been a labor of love for me to be part of, and this is actually my 15th year. So it's really, and to have this Jim Peebles be our speaker is really special. Professor Jim Peebles must like it here in Princeton. He graduated from the University of Manitoba in 1958, then completed his doctorate from Princeton University in 1962, and has been here ever since. When I asked for some fun facts, Jim said, you can often find me around town at McCaffrey's or at the Garden Theater. This was, of course, pre-pandemic. But that being said, he has received awards and prizes from around the world, from various universities and academies of science, the New York Academy of Science, the Royal Astronomical Society, awards from Toronto, Chicago, Manitoba, Astronomical Society of the Pacific, the UK, Israel, Geneva, Hong Kong, Stockholm, British Columbia, to name a few, and of course the Nobel Prize. In 1982, Jim Peebles was one of the first cosmologists to consider cold dark matter as crucial to the formation of structures such as galaxy clusters and galaxies. He's the author of 3 monographs on cosmology, and this is, I quote from Professor Peebles' Princeton faculty bio page. I continue to work in physical cosmology with preference for underappreciated issues. What might we learn from lines of research that are off the beaten track? They check accepted ideas, always a good thing, and there's a chance nature has prepared yet another surprise for us. I think we know that all too well these days. I'm pleased to introduce Professor Jim Peebles, Albert Einstein Professor of Science Emeritus at Princeton University and a 2019 Nobel Prize recipient in physics.
Thank you, Marian. It's a great pleasure to take part in this distinguished series, and such an important series in communicating what people are doing in physical science. Curiosity-driven, but still fascinating. So maybe we begin with the first. Am I connected? Hello? Here we are. So I arrived, as you heard, in 1958 as a graduate student. Einstein had died 3 years earlier. Oppenheimer was still director of the Institute for Advanced Study. I don't remember ever seeing him look so submissive. He was a wonderful person, really inspiring. And of course, he is part of a tradition of really great directors of the Institute leading up to Robert. I wish to talk about Einstein's thinking when he was much younger than this. The next slide shows you a picture of Ernst Mach, a philosopher and an excellent physicist. Here is a copy of his book in the English translation that I bought when I was a graduate student. And if you can get these pictures out of the way, you'll see that I paid $2.45 for it. Not a small amount for a graduate student in those days. There are in this book excellent demonstrations of what we'd now call classical mechanics. When I taught introductory physics, I used illustrations from this book. The book also has very pronounced opinions on the fundamental meaning of physics. In particular, Mach was one of the first to emphasize that motion has no absolute meaning. You're moving relative to something. And acceleration. When you step on the accelerator of your car, your head is pulled back. That's an effective acceleration. Acceleration relative to what? Mach emphasized that surely it's only acceleration relative to the rest of the universe. Let's look at the next slide. Here is a book Einstein wrote, or Einstein produced, from 4 lectures you may see at Princeton University, May 1931. This copy is in the Princeton University Library. The place is full of treasures, including this. I was amazed I was allowed to handle this crumbling book and to take this photograph of the front pages. In this book, Einstein discussed a problem he felt he had with Mach's ideas. Let's go to the next transparency. Einstein was very much taken with Mach's notion that acceleration is meaningful only relative to other things. But Einstein had realized that in his new theory of gravity, general relativity, there can be an island universe of stars like our Milky Way galaxy. And it could be in general relativity that there is no more matter in the universe, empty everywhere, space is flat asymptotically. This galaxy would have all the usual properties of inertial. If it was rotating, it would be flattened. Einstein disliked this notion. He felt that if the universe were constructed this way, then as you read, Mach was wholly wrong in his thought that inertia as well as gravitation depends on a kind of mutual action within bodies. You see that in this example, the galaxy would be rotating, but relative to empty space-time. To get around this, Einstein proposed a daring idea that there are no really isolated pieces of matter. The universe is the same everywhere, no edges, no special center. When Einstein published this idea in 1917, the Great War was in progress. Einstein was in Berlin, openly contempt. He felt this war is so absurd. How could we but agree? On the other hand, he could exchange mail with the Netherlands because they were neutral, and the Netherlands could exchange mail with England. So he was in touch with people who could give him astronomical advice on his great idea. On the next slide, we see an image, if you can find them, of Willem de Sitter with Einstein. This is a few years later. And in the next slide, Willem de Sitter was in the Netherlands. Einstein was exchanging mail with the Netherlands, with de Sitter during the war. He was also, through de Sitter, to England, exchanging mail with Arthur Stanley Eddington, seen here with Einstein a few years later. These people, Eddington and de Sitter, could have told Einstein about a book Eddington had published in 1914, the title, Stellar Movements and the Structure of the Universe. Eddington's universe was our Milky Way galaxy of stars. People knew perfectly well that this island universe of stars has an edge. It's not the same everywhere, by no means. In his book, the next slide shows, there are images of spiral nebulae, then called, and the speculation Eddington offered, which was on the mark, is that these are other island universes of stars. But people were perfectly well aware that these galaxies are not by any means uniformly distributed. The next slide shows what was known. You see the dots, these are individual galaxies. There's an absence of galaxies along the plane of this distribution because of obscuring dust in our galaxy. People weren't so sure about it then. But anyway, the view above and below is pretty clear, and you can see the great knots of galaxies. This does not look like Einstein's vision. I don't know whether any astronomer told him about this, and if so, whether he cared. Einstein had great independence of mind and great confidence. The beauty of his homogeneous universe seemed to outrule these minor facts. So I propose now to look at the present situation. In the next slide, you see an image of the whole sky showing our Milky Way. You see a band of light. The Milky Way is flattened. We're in the disk. As we look through the disk, we see the light from lots of stars. You notice also dark patches running through the bright regions. That's not absence of stars, it's the presence of dust that's obscuring the starlight. The next slide shows another galaxy of stars fairly nearby, a gorgeous image. Astronomers, you know, have a real advantage in vying for public attention. How could you not be attracted to this magnificent image? Do you see the dark lanes of dust running around the spirals? Do you see the blue regions? That's where stars had formed fairly recently out of interstellar matter. Among the stars, there are some that are much more massive than the sun. They are very luminous and they're very hot. Their light is blue. You see reddish regions. That's where massive young stars have ionized the interstellar medium. The plasma emits a radiation line in the red that makes them cause this red glow. You notice also a yellowish sheen running through the center that extends throughout this galaxy. It's the light of some 10,000 million stars similar to the sun. In our corner of our galaxy, there are at least as many planets around stars as there are stars. Consider, the odds are good that there are some 10,000 million planets in this galaxy that are on which all sorts of wonderful things are happening that we, the human race, will never see. Makes you think. The next slide shows you how the galaxy, oh no, it reminds you that there is another kind of galaxy, these blobs. And the next slide shows down below examples of large galaxies in our immediate neighborhood. You can see there are two kinds, these spirals that I've been discussing and these blobs that I've also been mentioning. This blob has eaten the spiral galaxy. You can see the dust running through it. Well, that's the way it goes. I think I can get rid of this, yes. This shows the distribution of galaxies near us. On the left, you're looking at the distribution of galaxies in the sky. On the right, you're looking at what you would see if you could look from 90 degrees to the side. You see 16 red dots. Those are the bright galaxies of the sort indicated down below. You see many more black dots that are less luminous galaxies, some of them a lot less luminous. You see that vast empty region to the upper left? There are a lot of galaxies in this neighborhood. There's only one in this vast empty region. I'm not sure, we don't really understand why that is, but as it is, what can you do? Here is one little dwarf galaxy in there. A subject that I've been trying to persuade my colleagues is worth careful study. What is it doing in there? Astronomers have so many things to look at. But let's look at the next slide. That shows you the clumpy distribution of galaxies, but looked at a larger scale. This is a sample drawn from the catalog of the brightest million galaxies obtained by an astronomer, Donald Shane, at the Lick Observatory in California. He and his colleague, Carl Wertman, spent 10 years from the late 40s to the late 50s, 10 years, scanning photographic plates with a traveling microscope to make the data that went into this image. I and graduate students here made this image. It was my great delight to take it to him, show him, and ask him, so is this what you saw? He laughed and said, I was looking at this one galaxy at a time. You see marvelous things here. You notice the bright patch just to the right of center. It is a great cluster of galaxies. It is, in effect, a galaxy of galaxies of stars. You see other bumps and wiggles across the way, but you also see something new. It looks much the same in the left and the right. We can get a still deeper, further, greater image of this by looking at the next slide that reminds you that some galaxies tend to have explosions in their center, somehow connected with the presence of massive compact objects, we suppose black holes, in the centers of large galaxies. You see that this galaxy has exploded and sent out a relativistic jet of matter. The next image shows another galaxy that had a really spectacular explosion. The galaxy is buried in the center. These two great lobes of plasma are radiating radio waves. It makes this thing visible at enormous distances. And so a map of the distribution across the sky of these sorts of objects shows us the really big picture, which is seen in the next slide. The big picture. I have to caution you about a few things. There's a hole in the center. That's simply, the instrument couldn't reach that part of the sky. There's some empty parts to the upper right. That's where they ran out of steam for technical reasons. Didn't observe there. You see a hole down just below center to the left slightly with a dot in the center. That's that immensely bright radio source you just saw. It's so bright that it confuses the telescope when it's looking in that general direction. You see a band of dark running to the right from that spot. Those are galaxies in our Milky Way. So as all those details aside, you look at this and what do you see? Nothing. You see Einstein's vision. Amazing to consider, somehow intuition can lead to aspects of reality. Don't depend on it. Lots of intuitive ideas Einstein had were wrong, and we're not Einsteins. Still, on occasion, it works. Here it is, Einstein's universe. Now let's consider in the next slide that the universe is said to be expanding. I like to point attention to the fact of Percival Lowell. Perhaps you remember that beautiful poem, "So now we are in Boston, the home of the bean and the cod, where the Lowells speak only to Cabots and the Cabots speak only to God." He was one of those Lowells. He became fascinated with astronomy and with the idea that there are canals on Mars constructed by some sort of advanced civilization. Astronomers honor Lowell's memory for deciding to build a telescope to look for these canals at a good place for astronomy, not a convenient place for where he lived, in Arizona, Flagstaff, Arizona. And he hired competent astronomers to instrument and use his telescope. That includes Melvin Slipher, who with great technical skill was able to measure spectra of galaxies and discover that the light seemed to be shifted toward the red, as if the galaxies were moving away from us. You all know the effect. You stand by the side of the road and you hear a car passing, ba-room. The sound of the engine isn't changing, but as the car rushes towards you, waves of sound are compressed, raises the tone. As the car races away, waves are stretched, lowers the tone. Same with light. The galaxies are moving away from us. Henry Leavitt showed astronomers how to measure distances to galaxies. Lower right, we see Albert Einstein visiting Caltech, California Institute of Technology. It brought out the suits, of course, but in particular, it brought out Edwin Hubble and his associate Milton Humason. Those two had just the right set of skills for the late 1920s through the 1930s to make great advances in astronomy, and in particular, this notion of an expanding universe. So the next slide shows the notion of an expanding universe. You saw Professor Dr. Willem de Sitter earlier. He, in 1930, wrote an article in a Dutch newspaper. We'll get around to that wording later. For the moment, I want to explain to you his elegant illustration of an expanding universe. Pretend for a moment that you live in 2 dimensions, not 3. You live on the surface of this balloon. Don't ask what's not on the surface. You live on the surface in 2 dimensions. There are galaxies everywhere. I guess that's what those squiggles are. You sit on one of them. Now, Professor Willem de Sitter is blowing up the balloon. Careful to understand, you're not expanding. The galaxies are not expanding, but the galaxies are moving apart from each other. You stand on a galaxy, you look around, and you see the other galaxies moving away from you. You say, wow, the universe is expanding, and it's expanding away from me. But of course, wherever you stand on a galaxy, you see the same thing. This is a homogeneous universe, uniform everywhere, where everyone has the same experience. The galaxies are moving away from us. That's the expanding universe. The next slide shows some of the people who developed the theory of this expanding universe in Einstein's general relativity. Hermann Weyl had the idea, a brilliant mathematician, ended up at the Institute, but he didn't have a theory. Alexander Friedmann, a Russian, had the theory, but he didn't know about the observations. The Belgian Georges Lemaitre, a priest of the Roman Catholic Church, a brilliant physicist, knew the evidence from Slipher. He independently developed the theory. He predicted that the universe is expanding and the galaxy is racing apart from us, the rate of racing away being proportional to the distance. The next slide shows what I like about Lemaitre. He in the years around 1930, understood Einstein's theory of relativity better than Einstein. But it happens. He tells why he finds no conflict between science and religion. The next slide shows a statement that I really admire. I'll let you read it, and I'll just give you the man on the street version. If a Christian decided to swim in a way that non-believers practice, there is great danger that the world will soon be short one Christian. If you want to swim, you'll swim the way believers and non-believers found practical. If you want to do science, you will do science the way believers and not believers do science. I'm not religious, but I really admire this religious person. The next slide. Well, so far we have the notion of an expanding universe, and we have some evidence from the motion of the galaxies. But that's a long shot. Do we really believe this? Well, during the Second World War, this temporary building was thrown up on a back lot at the campus of MIT in Massachusetts. Standing in front of it is Ray Weiss. You may know his name and face. He is a Nobel Laureate in physics for his central role in construction of the gravitational wave detector LIGOs that recently made a remarkable advance in detecting gravitational waves from merging black holes emerging white dwarfs. He is pointing to that building because on that building, during war years, there was a photograph taken in the next slide of Bob Dickey standing to the right with some colleagues and checking out an invention of Bob Dickey's during the war called the microwave radiometer. It can measure thermal radiation. In fact, it's detecting radiation from that shaggy thing Bob was holding. During the war, he took this thing down to Florida to check out the possibility of radar at shorter wavelengths. Radar was one of the big advances in this laboratory during the war, and of course, an enormously influential device during the war. He went to Florida to check out the effect of water vapor on shorter wavelengths. Florida is a good place to do that. He put even limits on what he termed the temperature of space. He put limits on the notion of a universe that is filled with radiation. The next slide shows that in 1964, Bob Dickey, standing on the right, had the brilliant idea that one could build a radiometer, one of his inventions during the war, to look for radiation that would be left over if the universe were expanding from a hot, dense initial state. On the left, you see David Wilkinson. In the middle, me. We two, plus Peter Lowell, were invited by Bob Dickey in 1964 to consider the idea of this hot Big Bang. Bob said to Peter Lowell and David Wilkinson, why don't you two build a radiometer to see if this radiation left over from a hot early universe is really there? And he said to me, so casually, why don't you look into the theoretical implications? So Peter went off to education and the use of computers in classrooms and laboratories. And David and I just followed that casual advice for the rest of our careers. It happens sometimes. The device in front of us, you know, those are actual musical horns, but they're also good for detecting radiation at microwave wavelengths. Flown from a balloon to show just how smoothly distributed this radiation is across the sky. The next slide shows another measurement. Dave Wilkinson was involved in the left-hand measurement. The whole point of this radiation left from the early universe is that it would be thermal. That is to say, you tell me the temperature, I'll tell you the intensity at each wavelength. Demonstrating that this radiation detected by David Wilkinson and others is thermal, requires measurements at lots of wavelengths. That's not easy to do from the ground because the atmosphere is radiating. You have to get above the ground in a rocket, or even better, in a satellite. Two groups managed to make this measurement. It took each of them 15 years. 15 years. One group was centered at NASA in the USA. The other group, led by Herb Gush, was centered at the University of British Columbia in Canada, my home and native land. They completed their measurements within a few months of each other. Each established that this radiation is thermal. The NASA results on the left have less noise, but the University of British Columbia measurements on the right are just as good. Both showed us this is radiation that is thermal, surely from the hot Big Bang. John Mather got a very well-deserved Nobel Prize for his leadership of the NASA measurement. Herb Gush, equally deserving, got the deep respect of his colleagues. The Nobel Prize is a wonderful award. I'm so honored. But you got to bear in mind that there are so many possible people to award the prize to. These prizes necessarily are capricious. If you're a young scientist heading out, I urge you, don't judge your career by prizes and awards. If they come, wonderful. If they don't, you make your own judgment whether you really did what you could do. Don't depend on these prizes and awards. They'll come, they won't come, live on. Let's go to the next slide. The cosmological constant. Here is the situation. Einstein, 1917, a logical universe is uniform, the same everywhere. Of course, the universe is the same in all times. He didn't say that, but he implicitly took it. The universe is forever. Stars may move around, but the universe, no, the universe stays forever, surely. He had a problem with that in his theory. It wouldn't stay static. It wouldn't stay forever. He adjusted his theory by introducing a new term called the cosmological, well, he called it the cosmic term. It became known as the cosmological constant. He labeled it by the Greek lowercase letter lambda. Here is the lowercase lambda in this artist's impression, who wrote it backwards, who knows, artistic license. Nowadays, that term is called the uppercase lambda. I don't know why we changed. Some call it dark energy. Whatever the name, we don't understand it. The evidence is clear, it's there. Its meaning, a great mystery, a great prize to be won. Don't aim at the Nobel Prize, but aim at discovering the meaning of this cosmological constant. What it does is combat gravity. It pushes where gravity is pulling. Einstein didn't recognize that this balance is unstable. Slightest departure from exact uniformity, and things will grow less and less homogeneous, less and less uniform. Einstein did not have a satisfactory solution, but he did have a term that, as the next slide shows you, he came to hate. Here is a letter from Einstein to Georges Lemaitre. In response to a letter Lemaitre had written to Einstein shortly after the Second World War. Lemaitre was contributing to an article on Einstein, a book about Einstein's philosophy. I read to you the last line about the cosmological constant. I cannot help to feel it strongly, and I'm unable to believe that such an ugly thing should be realized in nature. You see the great power of intuition, sometimes wonderfully right, sometimes spectacularly wrong. Let's go to the next transparency. I have held your attention long enough. We could go on for several hours about how it was finally realized that that cosmological constant is there. But I thought I would save, I hope I have a little time left to save time for a few thoughts. As was mentioned, I spent sabbatical leaves here at the Institute for Advanced Study on 2 occasions. It was wonderful. The place had a good restaurant. It had these beautiful grounds in which you could wander and ponder. It had offices, colleagues you could talk to, but of course you could just close the door to your office and get to work. When I came on two separate years, it was as if, perhaps you remember the play and the movie Brigadoon, where every 100 years, this wonderful village appears on the beautiful hills of Scotland. I considered approaching the Institute to be approaching Brigadoon. We might turn off the slides now as I offer just a few closing thoughts. It is remarkable to me that nature operates by rules we can discover in successive approximations. I don't think there was ever any guarantee it'd be that way, yet it proves that the theory Einstein invented a century ago now passes demanding tests in the laboratory, in the solar system, in the discovery of these merging black holes and white dwarfs that produce the gravitational waves that his theory predicts, in the theory of the expanding universe. Quite remarkable. Yet that's the way nature works. It's another remarkable thing is that I have spent my life producing something that is not monetizable, as best I can imagine. Why have I been supported by the university and the institute to produce nothing of intrinsic value? Well, of course, I think we agree that there is intrinsic value in the satisfaction of our great curiosity about what's happening in the world, among our neighbors, in our country, in the world, in the solar system, in the galaxies, in the universe. Deep curiosity, and remarkably enough, we can be satisfied, at least in part, bearing in mind also, of course, the fact that we'll never be satisfied. Consider all those planets on all those galaxies we'll never visit. Thank you.
Thank you, Professor Peebles. That was enlightening, interesting. I have a page full of notes that I took. We'd like to open up the floor to questions. If anybody has, we'll have a few minutes, about how many, I don't know how many minutes we have for questions, but just go into the Q&A on the bottom and type it in, and I will be happy to get the conversation started. Okay, first question, are galaxies being created in the universe as we speak? And do you, well, I'll give you the two. And do you believe that other life exists in our universe?
Right. So it doesn't look like galaxies are being created anymore. They all look old. And there are clouds of hydrogen that would, you imagine, coalesce into a galaxy. But without exception, as far as I know, there is not a cloud of galaxies that doesn't have toward its center a group of stars that are old, meaning it looks as though the epoch of galaxy formation is past. Now, you know, I have a slight allergy to the word belief because it has so many connotations. So, and I'm an empiricist, I love evidence. And, you know, there is a star nearby, 4 light years, I'm not sure I'll get the name right, 4 light years away, that has a planet that's just such a distance from the star that water on that planet would neither freeze nor boil away. Wouldn't you just love to see what's on that planet? And at 4 light years, it's not quite inconceivable that someday the human race will know. Send a whole flock of drones, a few of them will get near the planet, take an image, send it back. 4 light years after that, 4 years after that, we'll get an image. We'll discover eventually that is not a secret that is hidden. And certainly the discovery of life, in the moons of Saturn and Jupiter would be so moving. And to discover life on a planet on another star, wow. But it will take time.
We have a list of great questions here. The next one is, how do your thoughts differ from that of Stephen Hawking's?
I don't think they differ much. He, of course, is a deep theoretical thinker. I'm more into the empirical side of things. But, well, I have seen evidence of the extreme power of his inspiration to disabled people. Such an inspiring figure. I met him first when he was still able to stand and speak. I saw his deterioration through the years, but I deeply admired his determination. He stuck to it, to the bitter end, the wonderful end. He liked ideas of universes that began without a boundary condition. He had beautiful ideas. I have ideas. That was beautiful.
Thank you. What is your view of Einstein's, of Einstein's skepticism regarding quantum mechanics?
Well, he had a good point. This is really quantum mechanics. And you know, Einstein consistently emphasized that he recognized the great power of quantum mechanics. It's a wonderful theory, but he was convinced it's only an approximation. In fact, when you pause to consider it, all of our physical theories are approximations in the sense that if you apply them to the wrong situation, you get the wrong answer. We have approximations. Is quantum mechanics a final theory? I doubt it. Will a final theory replace the indeterminacy of quantum mechanics with something better, more aesthetic? I have no idea. I sympathize with Einstein's point of view totally, but you know, I've taught quantum mechanics on quite a few occasions. It's a wonderful subject. Will it be improved? Well, I certainly hope so.
Thank you. Where do you stand on the possibility of Einstein's unified field theory?
On the sidelines. I want a dream, and it's a dream that has been very heavily pursued. In the latest version, of which Director Robert Jagraft is an expert, sounds wonderful. You know, I spoke of intuition, and along with intuition are guidances from what has worked before. When Einstein introduced his general theory of relativity, his theory of gravity physics, we had a theory of electromagnetism that worked wonderfully well. Already, it was being widely applied. In short, electromagnetism was understood wonderfully well. And Einstein's general relativity theory is arguably just an extension of electromagnetism. You add another field. We call it the metric tensor. It measures space-time curvature, but it is just a field the way the electric and magnetic fields are fields. They both satisfy a differential equation that's about as simple as you can imagine. In short, I think Einstein had a working model for what to do about gravity physics. And in the same way, as I understand it, superstring theory had a working model. All of the wonderful physics of particles, the standard model of particle physics, wonderfully successful, beautifully detailed, but surely incomplete. It's a working model though, and people like Director Jagraft are pursuing how to follow that generalization. Are they on the right track? Well, time will tell.
Thank you. You may have, this might be part of one of the answers that you already gave, but what theories of Einstein stand out the most regarding becoming factual to the present day?
Oh, every time quantum general relativity theory, just startling to me to consider that he made that up. He had the guidance of electromagnetism to be true. He had that wonderful observation that particles of different character fall at the same acceleration. He had that hint. He invented a theory. He had virtually no checks of it, and very few appeared until the 1960s. Now that theory has been checked over an enormous range of scales, and it works. It's to me quite astounding that that construction from pure thought, so to speak, is so accurate. He did do some good things with quantum mechanics.
Thank you. A question about the Perseid meteor showers. Why do we always see them in August in the Northeast?
I'm no astronomer. It's true. I'm born and bred in physics. I have never taken a course in astronomy. I have to admit that as a kid, I admired the starry skies of Manitoba. You know, out in the prairies, in the winter, the sky can get wonderfully clear and the stars just stand out. But I never took an interest in them. I did admire the northern lights, which of course we were far enough north to see glowing in the sky, dancing at times. But and I remember seeing on occasion those showers of meteorites. Wow, what's going on? But I was much more interested in, playing around with electromagnets. So I will not attempt to embarrass my astronomy friends by trying to explain the Leonid and other showers.
It's always wonderful if we can catch it with the weather.
Yes.
So could it become an issue if galaxies continue to expand and push away from each other?
Oh no, in fact, I guess as you're aware, the evidence is clear that cosmological constant Einstein introduced is taking control of the motion of the galaxies and causing their motions away from each other to increase. We eventually, our Milky Way will be in splendid isolation. No need to prepare for that. It will take time, but that's the prediction. You know, I love considering the way the universe used to be because it left fossil evidence. I find it less exciting to think about the way the universe will be because it hasn't happened yet.
Okay, thank you. Let's see, is the speed of light travel theoretically possible?
No. Travel at a tenth the speed of light is very expensive. A lot of energy needed to get something moving that fast. There is talk of sending drones to this planet on this other star that would be accelerated by light pressure, but the drones would be tiny and they would move that fast. And so they take 30, 40 years to get to the planet. We can wait that long, but you don't want to push it to the velocity of light.
Okay,
Unless you're light.
So most of us can check that off as not something we're going to be doing. Let's see, have the years you've spent contemplating the universe changed your outlook on human life?
Well, I suppose so. It has made me more aware. You know, I grew up in the splendid isolation of Winnipeg, Manitoba. I didn't know about the world. And the fact that I have been doing research has meant that I get to travel to many parts of the world and admire the wonderful variety of societies that I've seen. In that sense, indirectly, my science has led me to see that the world is a wonderful place. A place that is, of course, terribly at hazard, but we mustn't get into politics.
Correct. That was the deal. What was the next question? What was the main reason that a cosmological constant concept was introduced?
There were two reasons, two observations, measurements. First, astronomers can measure the rate at which galaxies are moving away from us by that Doppler shift I mentioned. They can, by working very hard, measure distances. And you put those pieces together and you get the impression that, and remember also that when you observe a distant galaxy, you're observing it as it was in the past because of the time light takes to travel from there to here. So one has a history of the rate of expansion of the universe. That history showed, apparently, that the expansion rate recently has changed from slowing down due to the action of gravity to speeding up due to the action of that cosmological constant. That was a brilliant measurement for which I saw a photograph of Adam Rees earlier. He with Saul Perlmutter and Brian. My good friend Brian received the Nobel Prize a few years ago. Second measurement, the distribution of microwave radiation across the sky, that radiation from the early universe carries with it information about its past history. The decoding of that information succeeded in making a very good case for the presence of this cosmological constant. The fact that one had these two measurements, independent, both pointing to accelerated expansion, provided an awfully good case that the cosmological constant is there. We still don't know what it is, a subject of great debate, but that it's there seems beyond reasonable doubt.
Thank you. Let's see, can you clarify the question of within what is our universe contained?
Ha! Remember that balloon? And remember how I urged you not to think about what's outside the balloon? So now it's the same with us. Advanced ideas in superstring theory and related topics have a universe with 11 dimensions. Marvelous thought, beautiful. And who knows, maybe it's on the right track. But all you need for what we know now is our 3 dimensions of space plus time. That's it. That's all we need. That's not the final story. I don't think there are final stories. That's the story that works now. Wonderful ideas about other universes and all the rest, extra dimensions, to be explored. But what's established pretty convincingly is us in 3 + 1 dimensions. So live with it, unless you want to think further.
I guess moving's not an option, so. Do you feel there is enough unknown about inflation and early cosmology to allow for the possibility of some form of a cyclical model of the universe to be considered reasonably viable?
Yes. That sounds like an informed question.
Is there, okay, that's your answer, Alan. There was a person who had asked the question. Let's see. If you could be reborn, what would your most interesting topic be that you would want to explore?
I don't know. I've always been attracted to physics, always.
So that's something when you were a child, or like when you started thinking about what, I guess when you could start thinking about physics, at what age that is?
Although, I guess I just let you know how these things work out. As a kid, I loved to build things, but you know, I was not a very attentive kid in school. The result was I wasn't at all sure what I wanted to study at university, so I enrolled in engineering because I had the impression engineers built things, and I like to build things. It was okay. I learned a lot in engineering, but I remember in second year engineering, talking to a friend from high school, Dale Leverage. He doesn't quite remember this, but I think it's true. I said to him, well, engineering is okay, but I'm running out of physics courses to take, and those are the ones I really like. He said, why don't you transfer to physics? And I said, duh. It hadn't occurred to me. I transferred, and it was wonderful. What would happen to me today if I were at the university? I'm not sure I'd go into physics because it's been rather heavily developed. The life sciences, molecular biology is just so overwhelmingly important, practically, so overwhelmingly fascinating as a science that I think I might go there. It would have to be something where I don't have to deal with a cadaver. something more in what do they say? In glass, not life.
I always say it's as equally important to know what you don't want to do as it is to know what you do want to do.
True enough.
If you could share with us some of the projects that you are working on right now, and let's see, there was another follow-on, or working with the issues you're working on right now, problems you're trying to solve.
So I grew up in physics working alone because there weren't many physicists doing what I do. So I've not learned to play well in groups. I've never been in a large research group. Much of the action in cosmology these days is in large research groups. God bless them, carry on, but I don't want to do that. There are still small problems in astronomy, endless. Particle physicists have only one proton to deal with. They're all the same. Astronomers have galaxies, each of which is different. They have endless things to look at and endless things to learn from what they find. Difficult to learn the evidence. All kinds of things can be done, even by an individual like me. So I'm still thinking about small problems in astronomy. But right now, I have resolved to write a lengthy essay, maybe a small book, on the fundamental nature of physical science. What are the starting assumptions of physical science? What are the rules by which we operate? And what are the criteria by which we decide whether we're making progress? These are fairly straightforward things, I think, but things that, in my experience, we don't think about. We're too busy doing the science. And so I have been spending the last several months hacking away at this essay on the fundamental nature, the basic nature of our enterprise. It begins with a remarkable optimistic assumption that nature, reality, operates by rules we can discover. No one ever told us that. We have blind faith in it. And I have no objection, but we ought to write that down. So that's my starting statement. I'm working through the details.
Thank you. We do have a number of other questions. I just want to check with you on your time and how much.
I'm easy.
Okay, keep it going. Okay. Let's see. Do you know David Bohm, and what is your opinion of his work?
Bohm, the expert in quantum mechanics.
I'm assuming BOHM.
Yeah, well, I think he's passed away by now, surely. Is he still with us? I never met him. I have his book on quantum mechanics. It's a beautiful book. He turned to a notion of how to make quantum mechanics causal again. I've never been much attracted to it, but I certainly admire his efforts. But I can't say further.
Let's see. What are the most unorthodox lines of scientific investigation that appear to be promising, in your opinion?
Well, in cosmology, we have a pretty well-developed subject now, and people are working on the finer details, such as what in the world is the nature of this dark matter? I didn't get into that, but it's a long story. It is now a hypothetical component. It's got to be there to make sense of all the evidence, but what is it? And what is this is this cosmological constant? There are, though, side issues. Because we don't really understand the nature of dark matter, we've got to be prepared for surprises, because we've given it the simplest properties we think we can get away with. If it's any more complicated than that, we're going to run into problems, and we're going to learn something. One line of evidence that I'm fascinated with, but it's not terribly popular, I even perhaps annoy people, is the properties of the nearby galaxies. There is a large research effort going into studying galaxies at large surveys of galaxies. They're brilliant. Methods of artificial intelligence are being applied to sorting out the information you get from these enormous samples of galaxies. Great science, but yet necessarily each galaxy is treated rather schematically. I am increasingly fascinated by the fact that we have nearby galaxies that can be examined in enormous detail that may teach us something that you can't get out of an enormous sample of rather schematically sampled galaxies. That's not popular these days. It's fascinating to me. I've been enjoying doing that. And I must admit, it's kind of fun to annoy your colleagues in a polite way. The really controversial notion is of someone mentioned an oscillating universe, expanding, contracting, bouncing. A colleague, Paul Steinhardt, next door, has ideas along these lines. They're not popular. They're certainly worth pursuing.
Interesting. So something to just envisioning an oscillating galaxy.
Yeah.
So what is your opinion on commercial operations like Tesla and SpaceX and their ambition to colonize other planets?
Two parts of the question, of course: commercial and get out there and do something. I'm no judge of whether private industry is better than a well-organized government, which I'm not sure we have now, at this sort of operation. I leave it to well, Tesla, you know, is a wonderful operation, really impressive, but it is driven by the profit motivation in the end. Mm-hmm. And does that not sound a little scary when you're sending people into space? It's true the airlines have spectacular records of safety, except of course when they don't. Mm-hmm. We all know that story. Space flights by commercial operations have a wonderful success story, but are they going to continue to pay the obsessive attention that's required? Well, I don't know. I don't know how to judge that. I hope the government, when well organized, has a part in it.
Okay. What is your advice to young high school students who are just embarking on their scientific or on their science journey?
Look around. Try to find something that really fascinates you, and take your time at it. Don't rush in, as I did, to engineering when I was really meant for physics. Look around, take your time. The notion of a year off was not current when I was an undergraduate. I can see benefits. A grandchild is doing it even now. Look around. If you're lucky, you'll hit on something that really grabs your attention so strongly that you will be willing to spend your life It happened to me. It could happen to you.
Good advice. So how does imagination is more important than knowledge relate to your statement that we will never visit all of these planets?
Well, I don't know. Knowledge is important. Einstein made some mistakes that he could have remedied by reading the literature more carefully. He was well known, of course, for his independent thinking. He didn't care what other people thought. Very confident of it. A consequence was that he didn't follow the literature, so he made mistakes. I don't follow the literature either, because when I was active in this subject in the early days, there wasn't a literature to speak of. Hard to make the call, isn't it? I've forgotten the question, you know. What was the question?
The question was, let's see, hold on. Where did it go?
Oh, never mind.
Yeah, it might have been, I think it's gone.
Oh, well,
Sorry.
gone from my mind too.
Okay, let's see. Do you feel that each individual exists in different dimensions as Einstein stated?
Individual? I think this is getting a little confusing. You and I live in the same world. Agreed?
Yes.
I hope so. I'm not sure what the question means.
Okay, if it's unclear, we'll move on to the next one. Let's see. What is your opinion of global warming, or as I say, climate change, and how it will affect the long-term existence of life on Earth?
You know, I am not an expert in atmospheric science. I can only offer general comments. First, it is clear that we have changed the Earth's atmosphere and surface quite dramatically. It is also very clear from the geological record that climate on Earth is unstable, bounces around. There was a time when the Earth was covered with ice, snowball Earth they called it. There were more recent times when much of the country of Canada was covered by massive glaciers, a mile thick. We're in a remarkably tranquil period where the climate is pretty stable. What will happen as a result of the way we've changed not only the atmosphere, but the surface of the Earth? I don't know the answer. I'm not sure anyone does. The attempts to analyze the effect are so complicated that they can only offer us hints to what to pay attention to. But one thing I think is very clear, even to an onlooker like me, we are unintentionally doing a very dangerous experiment.
Okay, sobering words. And just for your final question, if you had a chance to ask Albert Einstein anything, what would that be?
You know, when Einstein introduced his notion, as I said in my talk, that the universe is the same everywhere, any competent astronomer could have said, "Come now, Albert." I found no evidence that any astronomer did say that. "Come now, Albert, we look around us, we don't see your uniform universe." I would love. Well, you know, I can't talk to him, at least in this world. I have asked historians on quite a few occasions, pestered historians, surely someone has left evidence that they told Einstein or that Einstein asked them about the astronomical evidence. It's got to be there somewhere. I'm aware that Einstein's correspondence has been wonderfully carefully sifted for all information. But have they uncovered every rock? I keep asking. I have not yet found any evidence that anyone had the temerity to ask Einstein what in the world he was talking about in this uniform universe? I'd love to know the answer.
Well, I want to thank you so much for sharing your knowledge, your thoughts, your opinions. And we are so appreciative of you taking the time to speak with our audience.
I enjoyed it. My final advice is, with Einstein, remain curious.
Thank you. Peter?
Thanks, Marian. Jim, I got to tell you, that was one of the more fascinating presentations, and I'm really fascinated by the questions and answers. They were just great. We really appreciate that the father of modern theoretical cosmology took the time to speak to our audience and gave us your opinions of what's going on. It was just wonderful. I also want to just say in closing that, again, I want to mention that these programs are brought to you thanks to our sponsors. I want to thank once again Bristol Myers Squibb, Janssen, GHO Ventures, and Novo Nordisk, who are leading companies in our region. I also want to recognize our promotional partner, the Institute for Advanced Study. Clearly, that is the place that great minds go to think and learn and just ponder what could be. I also want to again thank Professor James Peebles. I want to thank Marian Reinster. Again, this young lady has driven this program for the Chamber for 15 years, and that is just unbelievable. I thank you from the bottom of my heart. And for everybody who attended, I think you had a great opportunity to hear from a phenomenal lecture. This is what we try to do with the Albert Einstein Memorial Lecture Series. Present people who you wouldn't normally hear with topics that are fascinating. I want to thank you all for coming in. Enjoy the rest of your afternoon and talk to you all later. Bye now.